Thank you for joining Transform the Impossible, which is India's first future tech meets sustainability podcast. Today, I'm super excited for this conversation because we're going to be talking about the subject Cosmogenesis. A few years back, I came across this article which claimed that a group of physicists have figured a way to build the entire universe in a lab. That the moment I read it, my mind was blown. That subject couldn't go out of my hand. I really wanted to have a conversation with the man behind it. So, Big Bang. Now, everybody knows that the entire universe came into existence because of the Big Bang, which happened 13.8 billion years back. Now, how did that happen? Well, theory suggests that an atom, which is 50 trillion times smaller than a single grain of sand, which was densely packed with energy, exploded. And that explosion created this ever-expanding universe of ours with everything that we know, the stars, the sun, the moon, the planet, Earth, and us, and everything. So if a minuscule atom could create this entire universe of ours, then the cosmogenesis theory of building a universe in the lab is not so crazy after all. So today I'm delighted and honored to have Mr. Eduardo Guendelman, who's the man and the physicist behind the cosmogenesis hypothesis. He's the professor at the Department of Physics of Ben Gurion University, Israel. So thank you, and it's a complete pleasure to have you on the podcast. So we know that the Big Bang created this universe and everything that we know. Now I've been caught up with this burning question that if the Big Bang, which was this minuscule atom, the explosion of this atom, which created the universe and everything, if that had to happen, what preceded that? What came before that? What existed before the Big Bang? Could you talk about that?
Okay, there are many ideas around what was before the Big Bang, right? One idea is that there was the inflationary universe, right? That we call the Big Bang when the universe becomes hot. Before that, the universe could, according to the inflationary universe, the universe could have been cold, and then there was like some scalar field that fell down, and everything becomes heated. Yeah, and then there are other models that ask even what was before even that inflationary universe, right? Then it becomes like more speculative, because even in the inflationary universe, usually you don't solve the singularity problem. You still have a singularity. So there are other models that says the universe, for example, emerged from a state that was always existed for an infinite amount of time. That's called the emergent universe, and then it goes into inflation, and then afterwards gets heated, all kinds of things like that. Or the origin of the universe could have been from a universe that already existed, like a flat space or something like that, and there was like a particle. And inside the particle, there was a region of what's called the false vacuum that has energy and pressure, but the pressure is negative. Somehow this is unstable, because the particle can be unstable, such that you become the natural thing for the false vacuum, which is needed for the inflation, is to expand exponentially, right? And this could be the origin of the universe from an elementary particle, because you start from a very small region of space, it expands, and then everything becomes homogeneous and causally connected, and then you solve a lot of problems in cosmology this way. There are people still that they don't believe in the inflation, but most people believe there was inflation.
So the entire universe is made out of atoms. Now these atoms, when they cluster, they become molecules, and then cells, and then tissues, and viruses, and then skin, blood, and so on and so forth. And so basically, these atoms make the outward universe of ours, which is the star, the sun, the moon, and everything, and us also. So everything basically is made out of atoms, right from the trees to us, the animals. Now, could you talk a little bit more about that? Because it seems there are four fundamental forces of nature: the weak nuclear energy force, the strong nuclear energy force, electromagnetic, and gravity. How does all these come together into creating this universe of ours? What's the process?
If you have all the forces excluding gravity, then you have basically conservation of energy, and you can transform from one kind of energy to another kind of energy, but you cannot really create so much, because you can just pay with some currency, and then you don't get money like that, right? Something. Now, when you enter gravity, the situation changes, because the energy of gravity is negative. So the energy of matter can increase as much as you want. So the fundamental ingredient to make the universe is not so much the other forces like electromagnetic, strong, weak force, but the gravity. Of course, everything has to go together, right? But the gravity is without the gravity, you cannot create the universe, right? From a small region of space. For example, the region of space that produces the wormhole has negative gravitational energy, and then the bubble that is expanding can increase its energy up to infinity, and it's always compensated by the negative energy of the gravity, right?
So you're saying that gravity plays the most important role in the process of universe creation. And would you also like to talk about negative energy?
Yeah, it's the false vacuum, which is called a false vacuum, has a positive energy but negative pressure. And for example, you get this very easily in particle physics. There is what's called the Higgs field. Lots of things produce vacuum energy. The Higgs field, for example, the 0-point energy of fields, right? All produce vacuum energy, right? And then this is the source of the inflation, right? But you need the source. This gives you the matter, gives you the source. The elementary particles theory always produce very easily this kind of source. And then the gravity does the trick of creating, with this source, creating a exponentially expanding universe.
So quantum mechanics, I think, is one of the most difficult to understand subject, if I may say so, because the classical world, or the macro world as we know it, is very different compared to the micro world. We know that the entire universe is made out of atoms, but once the atoms starts clustering and it becomes macro, becomes big, it does not show the quantum mechanical nature it should. But in the quantum nature, it's very, very different. For example, photons, these particles have dual nature. It can be a particle as well as wave. There's something really weird. For example, I mean, in the physical world, I mean, I know that I have this mic over here, And my sister, who's sitting in America, she's in New Jersey. She's got the same mic. Now, if I touch this mic or if I remove it from here, the same thing is not going to happen at my sister's house. But quantum mechanics says that this is what happens. This is super entanglement. That it's entangled in a way and it's sharing a communication, breaking the laws of super relativity. That is weird. And then the classical computer, we know that the computer functions with zeros and one, binary, like classical. That's very clear. But quantum computer, the functions with qubits, the zeros and ones are in superposition. So the information could either be 0, it could also be 0 and 1, it could be 1 and 1, or vice versa. So this is really difficult for a layman or layperson to understand that what is going on with this quantum mechanics. So as a physicist, would you like to shine light on this subject and explain to my audience in layman's term what quantum mechanics is?
Quantum mechanics is the departure from the classical theory, right, of Newton and even Einstein, right? The relativity theory is still deterministic. So you replace the concept, the classical concept that the particles go into a definite trajectory by a wave function, right? That gives you the square of the wave function, gives you the probability of finding this particle at any place. And then of course, you have a possibility that the particle has a probability of being here, or being there, or Schrödinger invented the concept of the cat, the Schrödinger cat. A cat can have the probability of being alive or probability of being dead. You get rid of determinism. It's all probability, right? So in order to check quantum mechanics, you cannot just check one event, because this is you have to check a sequence of events and see if it's according to the probability that the quantum mechanics predicts, right? So then,
can you explain double-slit experiment and what does the experiment suggest? Does reality exist, or everything is just an illusion?
Yeah, this is the point that the particle is defined by a wave function, right? And a wave function is like a wave. So you can do like an experiment in optics, right? In optics, and then you have a slit here with a hole here, a hole there. Then the light, right, would go to the other side, and then there is a source. The two sources from the holes, the two sources interfere, right? And if you have one hole, there's no interference. It's just everything is like coming. It doesn't have anything to interfere with. With the two holes, they interfere, so this produces a distribution of possible probabilities for particle in the where you're measuring at the end, which gives you optics pattern, right, with a maximum and then some oscillations, right? And then this gives you the probability of measuring a particle at the end, right? The square of the wave function, which is right. So this is the duality, the particle duality, right? It's a particle, is a wave, but it's also a particle. When you measure it, it's a particle.
And yes, exactly. So that's still weird, because how does a particle behave in a wave manner as well as a particle manner? And how does a conscious observer affect the trajectory of the particle? Now, these are really deep questions, and I don't think we really have the answers for it yet. We have conveniently come to a conclusion saying that, okay, let's not ask deeper question about how a conscious observer affects these particles, but let's just come to a consensus that it's called dual nature. So now that's weird. So, but anyway, would you like to explain to my audience what string theory is?
Usually you say that the particles are just particles, or point-like particles, right? Something like this. Even in quantum mechanics, you say that, okay, I have a wave function, but when I measure it, I measure a point-like particle. Now you say you replace this point-like particle by an extended object, which is a one-dimensional object, right? So you can say, which is called a string. And a string is has a characteristic number, which is the tension, right? And the string theory is very interesting. It has a lot of possibilities, but my personal opinion is that it probably something like this is the ultimate theory of nature. But I think you have to work it out a little bit more. Some modifications, as I said, right, something like this, are necessary.
Yes, some of the top minds are working on string theory to understand how this works, because these atoms, they're actually one and the same thing. The strings which oscillate around them and their positions of the oscillation makes them or gives them certain properties. Because of the oscillation at a certain degree or whatever, makes them an atom or a proton or a neutron, and gives them the different properties of gravity, mass, density, magnetism, electromagnetism, and so on and so forth. So yes, I mean, string theory is trying to bring about a single theory, so that things get a little simplified, so people get to know that, oh, it's not so complicated. It's just this atom and how its interaction with the four fundamental forces of nature gives rise to everything. So yes, the day we get to know, understand string theory and what this atom does, I think we will be on to some really, really great transformation for mankind. Now, cosmogenesis, I've been waiting for this, because the entire the talk is about that. It is about the subject cosmogenesis, and you being the man who's been behind this hypothesis of cosmogenesis. So for the people who don't know what cosmogenesis is, would you like to explain this in layman's term of how we can build a universe in the lab?
Yeah, as I said at the beginning, you create a baby universe by using this false vacuum that is the source of the inflation, right? It's source of the inflation, and the false vacuum. And as we mentioned at the beginning, the false vacuum is is not hard to find in particle physics. It's a state with the positive energy density and negative pressure. Then there is a contradiction, apparent contradiction, because if you put this source of gravity, this kind of state of positive energy, negative pressure makes the universe exponentially expand. But where is it expanding? There is a problem, because the universe, this bubble, if you want, that contains this kind of matter, cannot expand and displace the environment, because it has negative pressure. So if the environment has zero pressure, the bubble cannot displace the environment. However, it expands. So how do you solve that? It says you cannot solve it in a flat space-time. You have to solve it in a curved space-time. And the curved space-time that is exactly solve this problem is wormhole. So the wormhole geometry allows you to have something that can expand without displacing the exterior. But at some point, this bubble that is being created this way disconnects from the environment. So you could create the universe in the laboratory, but you are not going to see it. Only maybe the beginning. Afterwards, it just disconnects from your universe. Yeah.
So can we just stay on the subject a little bit longer and explain the process? What is the process of this? If we have to build a mini universe, a mini universe in the lab, say possibly maybe like an underground collider like the one which we have in Europe, CERN, what would be the process? What would be needed? I had read somewhere that you had mentioned that you might need a magnetic monopole. Now that monopole, this particle, it does not exist at this point in time, but there's an hypothesis that this particle exists, and maybe someday we will be able to find this particle. So what would be the ingredients and what would be the process of building a universe in the lab? What would be the process?
I think this cannot be. It would be require energies too high to. The only thing is where people were saying that the true scale of gravity is not what's called the Planck scale, which is very, very high, but it's smaller, and then you see effectively that it's another scale or something like this. But it would require a modification of gravity. It would be possible only, but not in the context of general relativity. It would be, you would have to modify the gravity to be able to have this in accelerator experiments. Not it's only if you admit that the theory of gravity is like the general relativity of Einstein, you don't have a chance to see this in a collider experiment.
So you're saying that currently it's not possible to build a universe in the lab because it will take humongous amount of energy, which we don't have at this point in time. And we will also have to modify gravity. Is that a possibility that in the near future, we will be able to build a universe, a baby universe in the lab? What would require to build a baby universe? Is it changing gravity? Is it the energy requirement? Is it having a large enough particle collider? Is it a specific particle that could create the baby universe? Because if they understand that the Big Bang happened because a specific particle densely packed with energy exploded into this ever-expanding universe of ours, maybe that could be a clue of finding or understanding the process, and maybe possibly then saying, okay, then maybe we can, if that's the process, that it was that specific particle which was responsible for building the universe, then maybe we have the answer that maybe that could be the particle that we require and the amount of energy.
Yeah, other ingredient is you have to have something that produces a wormhole geometry, right? A black hole, for example, has the possibility of producing a wormhole geometry, right? And then wormhole geometry is like you go from one space, from one region, and then you discover there is another universe, right? Something
right.
In another region. So this baby universe would expand in the direction of the other universe and disconnect. So you have to be able to create this. If there is no black hole, you can either generate a black hole or you could create a wormhole by exotic matter. Exotic matter which is not ordinary matter, right? It's like negative, all kinds of exotic matters that they don't appear in normal theory of particle physics, right? Something like that. But they could appear by quantum effects or something like this. But it's speculative, right?
Do you think it will be possible to create a baby universe lab in your lifetime?
Yes, but the question is, suppose that you create this baby universe. Since this one is going to disconnect, then you will have the burden of proving that you made the baby.
Exactly.
There were some people that said that you could do it. Yeah, you could do it because you changed the geometry. It's not exactly the geometry of a black hole, but so there is a way to see deep into the baby universe. Some people in Connecticut say that you could do it, but it's controversial.
I was going through your profile and it says that you, with your student Jacob Potnay, is studying questions relating to the possibility of generating a universe out of a very small region. So, what does the current understanding suggest, and where are you in your research at this point in time?
Yeah, we have been working also with my colleague Stefano Ansoldi, yeah, and then all kinds of models of creation of universes, right? That usually you have a threshold of some energy, mass threshold to start with, something like this. If you use string matter, for example, we have shown that you need very little energy to produce this kind of process. We have a lot of models, right, for child universe or baby universe production, but it's still everything is theoretical, right? We cannot do experiments concerning this. Right?
The art of creating a baby universe, it's such a profound thought, because if that is possible, you're actually playing God and you're saying that this is actually simple. It's not such a complicated process, that all you need to do is shoot monopoles in our underground collider with the speed of light, and when it clashes, the amount of energy that it might release would create a black hole. The black hole would detach from a universe and creates its own universe. And in that universe, there would be everything that we know of this universe would come into existence, like the stars, suns, moon, or its own planetary system, and possible Earth-like planets where there could be life. That itself is so mind-blowing. Now, how has the peer community or the media reacted to something like this? I know that Andre Linde, Alan Guth, and some other top physicists have been a vocal endorser or support of Cosmogenesis. But how's the support system been? I mean, how has the community or the physicists reacted to this hypothesis of Cosmogenesis?
Yes, there has been support. Also, maybe I should mention that I don't know if you know Zeya Merali.
Right.
She wrote a popular book. It's called Universe 2.0. She reviews all the kind of models. Yeah, using one of the models is using magnetic monopoles, right? Something like this. The field of a magnetic monopole produces a geometry that's very nice to create baby universe. Also, this was from a Japanese group in Osaka, and then I work also with another colleagues from Japan, right? On the a bubble which is oscillating, and then at the end it decays into a universe, right? So the universe from a breathing bubble, right? So we have many models, right? That each of them shows different aspects of these possibilities of creating a baby universe. Also, there is a possibility to use this creation of baby universe to understand the quantum gravity, because you have a lot of quantum gravity has what they call ultraviolet divergences that very high energies are produced. So we say that maybe this problem is solved by the creation of baby universe. These regions of very high energy just get disconnected from your universe, and then they don't cause any more troubles or something like that. They can help the quantum gravity to be well defined.
So you're saying that quantum gravity is going to play a huge role in case if you want to build a baby universe. Now tell me, I mean, if and when we are able to create a baby universe, would it look similar to the universe that we live in? Would there be life on it eventually? Would we be able to change things, manipulate things? Because we know that our universe is full of suffering. Would we be creating another universe which would look exactly like us? Would we be able to kind of tinker around a little bit so that we could correct the mistakes of our creator and be able to create, in process, create maybe a universe that's maybe better than this one? I'm sure this is my arrogance, but if that's a possibility, would we be able to kind of manipulate things and change things once we create this universe? Would we be able to change things for the better for this universe?
There could be many possibilities. Depends how you form and from what is the original material, right? It's, generically, any universe that you create will not allow life. Yeah, you would have to fine tune, as you said. You would have to fine tune the conditions.
How do we do that? What would be the fine tuning process? Because we know that we live in this universe, and it seems too very fine tuned for life. But how do would we be able to fine tune or create a universe that is fine tuned for life? Is that a possibility?
Afterwards, everything evolves. After you create the bubble, then the bubble becomes very, very big. So at the end, it's the universe evolves like as if there was no bubbles. It just evolves like a normal universe. So then you have the same questions that you would have in normal cosmology. Why this universe is so finely tuned, right? And all those things come. This creating the universe from a baby universe doesn't solve the question if you are going to make life more probable. It's just you will get all these problems the same way. Apparently, you cannot make changes because you can create it, but then it disconnects from your environment. So from the original universe, it gets disconnected. So you would have to find a way to go through the neck of the wormhole, right? But usually this is not possible. You get collapsed into the black hole, fall into the singularity.
So as a physicist, what got you interested in cosmogenesis? Why did you even think that something like this was possible? What was the nudge that forced you to kind of look into this and say that, oh, if this is the universe making process, then actually maybe we could build a baby universe in the labs? What got you interested in the subject of cosmogenesis?
Well, it was the time I was PhD student at MIT in the 80s, and then Alan Gush, who created the inflationary universe, was coming to MIT, got the job at MIT. I was an associate professor. And then we were discussing, so he has this theory of inflation. But then we discussed, we had this project of having the inflation locally, not the inflation happened everywhere in the universe, but like there was a bubble of inflation, and outside was just an empty space. And then we said, okay, the equation of motion of the bubble, we can calculate, because you can say you have a space inside, a space outside. A space outside is called the Schwarzschild space. Space inside is the Sitter space. We give some matter of the correspond to the bubble, which has like surface tension, and then we calculate the equation of motion of the bubble. And we were very puzzled, because how we make the bubble expand if it's a negative pressure. But then the geometry of the Schwarzschild space allow us, provided there was a wormhole. So that's how that was my first work on this subject, with my PhD thesis with Alan Guth.
What, according to you, are the most important questions in physics which haven't got any answers yet?
What I think is that is not very much explored is that usually physicists think that if you go to microscopic, that's the question, that's the answer to everything. So everything, what is what they call reductions, right? So, like people say, okay, we got the atoms, but then they say, okay, smaller than the atoms are the quarks, and then smaller than the quarks we have the strings. But I think this line of reasoning has been very successful. You say that everything, the laws of nature are found, first of all, in the most small scales. Not maybe always true. Because, for example, I was working in this string theories, something like this, in the way I modified. And then you see that you can introduce some kind of fields. And these fields are determined by some equations, something like this. But then if you, then I was introducing another field, what I call is associated with the tension of the strings, something like this. And these fields happens that you cannot determine if it's just one string is there. You need at least two strings to be probably in the same regional space, and then you determine. So this is just an example that you can make universe a little bit more complicated, and then like new forces or new effects can appear. The laws always existed, but they manifest itself once you get more and more complex. I think life should be an example of this, because obviously you don't have a life doesn't exist for an atom or something like that. But once you start making things more complex, they're emerging things, and like new laws of physics manifest themselves. The laws of physics should be the same everywhere, but they can manifest itself once you get something a little bit more complicated and stuff like that. So I would say the question is, can you find the new laws of nature, but not by going to the very, very small, but to examining a little bit more complex things. Of course, there is always the other direction, going to smaller and smaller scales, the smaller and smaller distance at higher energies. But unfortunately, this direction is very interesting. Yeah, you could do something cosmology, but it's a little bit restrictive, because we don't have enough money to construct the accelerator of the size of the solar system, stuff like that. But on the other direction, you could.
So that's a little surprising, because I guess most physicists are saying that to understand the world better, we need to understand quantum mechanics. We need to go at the basics of what the entire universe made out of. If it's made out of atoms, how does its clustering into the macro creates the macro world of ours? But yes, somehow, I mean, you're saying that we need to understand the macro world. And somehow, it's a little counterintuitive, but yeah, there is a little reasoning over there, because I mean, at least the quantum mechanical world, everything is so very weird. Everything starts making some sense to us when things become macro, when things become large, and that's the only time when we can actually understand or relate, interact with the world better. So, as a physicist, what excites you, and what are the things that you are most looking forward for? What are the things that you think that if we are able to kind of find answers to, we will create huge transformation in mankind?
Yeah, well, I'll try to find the new laws of nature. For example, even if you believe in string theory, I think the string theory is not finished. I think you can make modifications. Now, working on the string theory, using these modifications that we use with these measures and things like that, and you get new effects. And I was able to introduce new fields that are unknown. Just a month ago, I was writing papers on that. Try to do something a little bit different. Because the people that I think you can do this only if you're coming outside from the string theory, because the string theorists, canonical ones, they think this is sacred, so they don't want to modify it or anything. So it's very hard from the string theory to come down to a theory of gravity that is well defined and all that stuff. A lot of ambiguity. So you can just start with the theory and then work out all the possibilities. And then from this side, I have in observational cosmology, there are all kinds of things that do not match, like what is called the H0 crisis, that you measure the Hubble constant according to microwave radiation, or you measure it according to the redshift of the supernova and all kinds of things. And there you have to work like with effective theory. You don't say this theory is fundamental, but I just want to explain this phenomena, something like this. And then all kinds of phenomena in astrophysics and gravity. I work from this point of view, without starting with the string theory and then going down, because this is very hard. You have to work with some theory that you want to explain the data, right? So this is another direction I'm working in. Right? From the fundamental direction, say probably string theory. But then this is very hard to get to the observational data. You know? So, but then you can ask a conceptual question, fundamental questions, but they are not so useful to explain the universe that you really see. Because it's a very hard theory to get from the theory, the abstract theory, down to the nitty-gritty details of what you see. And the other thing is that you just work what we call phenomenological, right? Just want to put the dark energy, the dark matter. And we use for these models, these modified measures and all those things, because you can handle there the dark energy, the dark matter, all in a very nice way. So the theory is itself very nice, although it may not be fundamental. You say the hope is it comes from a more fundamental theory. But in the meantime, you compare with the experiment, this theory that you have. This is the other direction that I follow. Right?
Thank you for being part of the show and shining light on, I think, it is one of the deepest subjects that we know of. The day we are able to, you said, maybe fundamentally tweak gravity and have energy enough to create that experiment and see that if we can build a universe in a lab, I think it will be the day man will become God. I know there are a lot of complications, but if you see almost all of the technologies are right now becoming so powerful that it is going to give us godlike powers, whether it's artificial intelligence, whether it's genetic editing, whether it's quantum computing. Once these matures, it will be very difficult to fathom who we will actually become or what our future will look. Will we destroy ourselves with a hubris that, oh, we can also play God and create our own baby universes, or artificial general intelligence, or tinker around with the source code of life with genetic editing and create designer babies? So these are very, very deep and fundamental questions. I think we need to really tread on this subject very carefully. I mean, not just cosmogenesis, but also artificial general intelligence, genetic engineering, quantum computing, because these tools will no doubt give us godlike powers. Over the ages, over the history, we humans have not been really good with power. So thank you, Professor, for being part of the podcast and sharing your insights. I know we're at the step of, at the cusp of becoming God. I don't really know whether we are ready for it. So on that note, to my listeners, if you like what you see in here, please press the subscribe button. And until next time, see you guys. Bye-bye. Thank you. Thank you, Professor.